I'm Michaela, one of the student members of the Community Conversation series, and on behalf of University Housing, I welcome all of you to this evening's Community Conversations event, Molecular Gastronomy. The Community Conversation series is a living learning initiative of University Housing, co-produced by the students of the University of Oregon, or the Oregon Brain Tank, an undergraduate academic group in the residence halls. I also wish to acknowledge our co-sponsors, the Robert D. Clark Honors College, the Oregon Humanities Center, Undergraduate Studies, and the UO Libraries, who have collaborated with University Housing for the past 8 years to make this series possible. At this time, it is my honor to introduce our esteemed chefs and chemists. Chef Doug Lang with University Housing. Chef Dan Irvin with University Housing. Chef Dominic Sachet. Chef Chris Crosswaite from Lane Community College Culinary Arts and Hospitality Management Program. Randy Sullivan, lecture demonstrator with the UO Department of Chemistry. Finally, we wish to thank Tom Driscoll, Director of Food Services and Associate Director of Housing, for making this event possible. Please join me in welcoming our panelists.
All right. Okay, well, welcome. Thanks for coming tonight. I'm Doug Lang. And we would like to start off this evening with a demonstration of something in molecular gastronomy called spherification. And we're going to have our assistants here hand out some of these little salads we put together with microgreens. And these are, hopefully there's enough here. There's a lot more people here than I thought we'd have. Yeah, go around. Maybe you take that side, you take that side. So these are small salads with microgreens with those little caviar-looking things on there are not fish eggs. Those are actual, the orange one is carrot juice, the red one is tomato juice. And
now, Doug, if that was juice, it would be spilling all over the place.
Well, it's spherification. That is where we use sodium alginate and calcium lactate together to make this gel. And it's really a cool process that I just learned myself. So it's something that you're actually seeing. There's some books we brought here that show some cool pictures as well, where these, even the balsamic vinegar, the real dark little egg-looking thing in there, that's balsamic vinegar that has been gelled as well. And the little powder that you see in there is actually the olive oil that has been turned into a powder by using maltodextrin with the olive oil. So it's all totally edible. It's just a fun way to present food. And we can, actually Dominic here is going to do a demonstration. He has some carrot juice here with some sodium alginate in it, and he is dropping it into a water bath of some calcium lactate, and it's a pretty cool process. Chris is very familiar with how this takes place.
So the sodium alginate, it causes the liquid to get some viscosity to it. So it's not completely liquid like a juice would be. Then it's immersed into the calcium bath, and in that reverse spherification with the balsamic vinegar, those two compounds are reversed so that he's dropping the calcium lactate in the balsamic vinegar into an alginate bath, which causes a similar reaction, but the calcium lactate doesn't cause the balsamic vinegar to obtain any viscosity to it. So it's liquid inside, hence the term reverse spherification. So it's liquid on the inside. When you bite into it, it kind of explodes or pops in your mouth. Absolutely, I can.
All right, and while Dominic's working on that, we're going...
Dominic.
Yeah. I thought I'd show you a little bit about chemically what's going on here, because is you see we're mixing two liquids and getting out something, maybe you wouldn't call it a solid, but a gelatin out of it. This is basically similar. How many people here are taking chemistry right now? Okay. You remember first quarter when you did the precipitations, right? Same type of thing. We've got two liquids being mixed, and they're going to make a solid. Calcium is actually quite good for that because a lot of calcium salts are not soluble. And so if you mix something soluble, a calcium salt that's soluble with something else, a lot of times it'll precipitate out. Let's take a look at that. Right here I have some calcium chloride. This is a salt that's, if you ever come here on a day when it's icy, they spread calcium chloride on the sidewalks to melt the ice. So it's fairly safe. We're going to take some calcium chloride. As you can see, it's a clear, colorless liquid. Chloride is one of the salts of calcium that is soluble. Then we're going to add to it some washing soda, Arm & Hammer washing soda. This is sodium carbonate, not sodium bicarbonate. It's related to it, not baking soda, but washing soda. And we'll see what happens. Another clear, colorless liquid. Let's take a look. And as you see, we got a solid coming out of those clear, colorless liquids. One of you chemists want to tell me what that solid is? It's a precipitate. What compound? Calcium carbonate. Anybody know another name for calcium carbonate? Chalk? We just made some chalk.
The White Cliffs of Dover.
The White Cliffs of Dover is an easier way to get it. So what's going on here is we have another calcium salt mixing with the sodium alginate, and that makes calcium alginate. But instead of being a white powder, it's a gel. So when that gel forms, it can either make a solid little gel out of a liquid or make a little capsule around some liquid in the reverse spherification.
Exactly.
Thanks.
Great. And as Chef Doug mentioned, the olive oil, which everybody knows, salad has a vinaigrette dressing on it. Well, it could be cream dressing, but vinaigrettes are more healthy for you. So we did the vinaigrette dressing in a completely different fashion with the spherification, reverse spherification of the balsamic vinegar, and then we took the olive oil and made it into a powder using maltodextrin. Now, a lot of these chemicals that we're working with here, they are there. They've been in the food processing industry for a long, long time. It's never been in the forefront in the culinary world until recently, which is why most of us have never heard about this stuff unless you read the package of Twinkie and then you get all these funky chemicals, of which these are some of them. Come on, everybody's had at least one Twinkie. Right? Deep fried. Okay. Any questions about spherification? Okay.
Is there a limit how big you can make the ball of stuff?
Aesthetics, basically. You can make them quite large, and in fact, in a lot of applications in the culinary world, we'll use big tablespoon size scoops to set the spherification, and then that would be the appetizer, the larger portion. It just takes longer in the settling bath for the process to occur because it's a much larger sphere.
All right. Okay, how was the salad? Interesting? And the little crunchy things on there is called bubo arare. It's a little rice cracker, just to give it a little crunch. Okay, so our next demonstration is going to be on pressure. And this is it's a cooking process called sous vide, which means under pressure. And my voice is under pressure. So what we did tonight is we prepared some chicken breast with, it's with a coconut milk infused with lemongrass, some lime leaf, some ginger, some really good aromatics. And we prepared it sous vide. So what we did was we vacuum sealed it with this vacuum sealer here. And so basically this part, the chicken's already done. We're just showing you how we did it. We pour the aromatic liquid into the bag, and we seal it. And this contraption over here to the right, my right, it's called a thermocirculator that Chris was kind enough to loan us. And
Excuse yourself.
the whole purpose of the sous vide cooking is for precision in your cooking. And if any of the really high-end restaurants you would go to these days, just about all the proteins, even vegetables, are prepared sous vide, and it's to really control the cooking process, where this chicken would be heated to exactly 160 degrees and stopped. And that's where you can really tell the difference. We'll pass out some samples here with the chicken, accompanied with a sauce that's really a foam, another part of molecular gastronomy, where we took some of the infused coconut milk, and we charged it with the little nitrous oxide whipped cream dispensers. And actually, we have a little bit right here.
So while he's getting that, I just want to explain what he's doing here with the chicken breast. Once the chicken, or whatever the product is, especially proteins, have been sealed in the bag, we put a little strip of this white plastic high-density foam on it, which acts as an air and moisture barrier to put the thermocoupler probe into the protein. So now when he immerses it into the hot water bath, we can monitor the temperature of the protein to make sure that we're achieving the proper or desired temperature during the cooking process. Now, it's kind of like a double check system, because the thermocirculator will maintain a constant temperature, plus or minus 0.2 degrees Fahrenheit, of the hot water bath. Right now it's set for 160 degrees, and it takes about a half hour for this size of chicken breast to reach that temperature. And we just want to verify that by using the probe thermometer at the same time. So you want to talk about the foam?
Sure. The foam that we are going to be placing on these samples we're bringing out for you to try is it's really just an aerated coconut milk. It's the whole idea behind it is to give you that nice mouth feel, a nice fluffy, warm sauce. So it's something Dan here is actually shooting a little bit onto this plastic lid.
So most of us think of a sauce as being a thickened liquid that you put underneath or on top of your protein, whether it's animal or vegetable protein. So by putting the sauce component, the liquid, into the charger, and we've added two components. One is a modified soy lecithin called VersaWhip, and a gum called xanthan gum to give it a little bit of viscosity. So when you dispense it from the charger, you get that nice foaminess, but you also get some stability, so the foam stays. And as it comes around and you taste it, it's very light on the palate and intensely aromatic. And because it has the charged aeration in it, it also aids in the releasing of the aromas when you eat the product. Yeah. Push the button.
Thank you.
You're welcome.
Do that.
All right.
Hey, Chris, can I get back to the vacuum thing for a second?
Absolutely.
What's the purpose of putting the vacuum on the food?
Because it's cool.
Well, yeah, obviously.
No, the fun.
Buying a cool toy is obviously a good enough reason for any
That's right.
scientific process.
So
Or cooler.
the whole sous vide concept originated by a French chef who, good friend, was a chemist. And they discovered that by packing foods under pressure and then cooking them, you can achieve a couple of very important things. One is, because you've got this product under pressure, you're keeping all of the moisture and flavor compounds in the protein or in the product, whether it's vegetable or protein. So it's not going anywhere. It's not evaporating into the air. It's not leaching into water or anything. It's staying in the product itself.
Does it actually push it into the product?
It can. In fact, when we put the coconut milk in the chicken and then vacuum seal it, because it's under pressure, it's driving all of those flavor components of that marinade into the protein.
Now, I wonder if anybody else is confused as I am. He's saying it's under pressure, but we drew a vacuum on it. What kind of pressure is it under if we draw a vacuum? Somebody said it. What is it back there? It's under atmospheric pressure. And we think, oh, that's just the atmosphere. I'm around in that every day. That's not so much. I'd like to do a little demonstration for you to show you just how powerful atmospheric pressure is. Let me step around here.
So while he's heading outside, I just want to touch on one other very important aspect of sous vide cooking, and that is the temperature control aspect to it, cooking at a precise temperature, which will vary from product to product. And that is the objective with proteins in particular, is to denature the proteins. We perceive denaturing of proteins as tenderness. That's why we cook our food, is to unwind the strands of protein, breaking them into smaller chains, protein chains, so that it's easier to eat. So by controlling the temperature that we cook the food at to get it at the precise point that the proteins begin to unravel, we can actually increase the tenderness of the food products in that process, which is one of the side miracles of sous vide, is absolute tenderness without overcooking, maintaining intense aromatic qualities and excellent texture and moisture content. Thank you.
All right, thanks, Chris. If I can direct your attention over here, again, let's take a look at the power of atmospheric pressure. Out here we've got a drum contains about a gallon of water. It's been boiling for a while. So the drum's no longer filled with air. It is filled with steam. And so my assistant, Simon, is going to, first of all, shut off the gas.
Watch the cords on your foot. Thanks, Jane.
No, you. All right, and then he's going to cap it. You can use your fingers to get it started. There you go. Get it on there good and tight. That's great. That's fine. Now, Simon, if you would, grab that drum, and why don't you put it down over here? Young man, can I get you to step out of the way? And if everybody can stand back a little bit further against the wall. Further against the wall, there's people behind you. Then we're going to pour some water on it. Now the water is going to condense the steam so that there will no longer be any gas inside the cylinder, inside of the drum. And let's see if what happens here. It collapsed so hard it broke her spoon.
That was classic. That was so good. That was so classic.
And so you can see there the power of atmospheric pressure that's driving those juices into the chicken breast.
Right, and that is 1 atmosphere of pressure. Okay, the normal atmosphere you're experiencing right now is called 1 atmosphere of pressure. That's how powerful it is.
All right.
That was great.
So,
Give it up for Simon. He's been out there doing this for us.
yeah, I think that'd be a good time. We'll start put little picks in them. Or, I'm sorry, spoons. I'm sorry. Let me give you a hand here. All right, we have some little plastic spoons that we're going to put out with this ice cream here.
So good.
Are you going to be late?
Oh, so good. Yeah. All right. All right. So,
Got it?
all right. How was the chicken? Nice and tender? Yeah, that's that slow cooking process. That's all right. So, our next demonstration is going to be on making ice cream. And it's not just any old way of making ice cream. We have in this doer here is, if anybody can guess what it is, it's negative 196 degrees Celsius. Not dry ice, it's colder. Liquid nitrogen. So, we're going to be passing out some little samples for you to enjoy while we're making this. So you won't have to worry about this getting done for you. This is just for show. I mean, you can eat it when it's done. But, anyway, we poured some custard with just vanilla bean into this container. And with Dan's safety goggles.
Just before you go, does anybody know how ice cream is usually made? Right, you churn it in a machine that turns the custard or whatever your ice cream base is, and you've got either a refrigerant on the outside or you've got crushed ice with salt, which lowers the temperature, freezing point, which freezes the ice cream as it's churning. And that process can take anywhere from 20 minutes to an hour, depending on your piece of equipment. So now we're going to show you a much faster way.
Yes, this is really fast.
Go ahead.
Ice
All right.
cream in minutes.
Can your camera get in here? This stuff is so cold that sticking the ladle in here is causing the stuff to boil. It doesn't take much. Look at that. It's just dancing on the top of the ladle. Is it already done?
Yeah,
I think it's already done.
one more too.
One more. All right. This is something you don't want to get on your skin. Sorry it took so long. There you go.
Ice cream!
Now we actually have to put it in the freezer to warm it up.
Right. You actually can't eat it right away when it's this cold. It's so cold it'll burn your mouth.
You have a question?
Well, we worked ahead. We made some yesterday, and we put it in our freezer so it'll warm up so you can eat it. So we brought it over all portioned for you. So we're passing those around with little spoons in there for you. So we actually made some of this with using little syringes and these into just dropping it right into the doer of the custard, making Dippin' Dots. And it was a lot of fun. We wanted to do that for you tonight. That would have been a lot of dots to have to knock out in a small amount of time, so we went with the bulk version. But we're having a lot of fun with this. We hope you are too.
Now, Doug, we saw a lot of what looked like steam, but it was, of course, water vapor from the air condensing and the cold gases coming out. But I'd like to give a little bit of demonstration of just how cold liquid nitrogen is.
All right. All right. Brought enough for everyone.
Dry ice.
Need help with the spoons? Yes. Sure. I'll give you. Okay. Oh, is it too hard?
Yeah.
Wow. Oh my gosh, you got really hard.
Balloons, don't go leave home without them.
It's more dry ice than we used to use to pack the ice carvings on.
So I've just taken a balloon and filled it with air for my lungs, so it's a little bit depleted in oxygen, a little bit rich in carbon dioxide and water vapor and garlic from dinner. And we're going to take some of this negative 198 degree liquid nitrogen and pour it out. Now, remember that if the boiling point of nitrogen, remember air is 80% nitrogen. So we're adding a little bit of nitrogen to the air. No problem. Question? I have some gloves, but this is protecting me right now. This is room temperature on the outside. Always good to think about safety. Thanks for reminding me. I will when I try to handle this tray. So you got to remember this. So this surface right here is 250 degrees Celsius above the boiling point of this liquid nitrogen, so that when I pour it out, shouldn't you be wearing socks? Sorry. But you see, it's like pouring water on a hot skillet, and it's exactly like that. It boils very quickly. So we're going to take some and pour it onto this balloon, and you can guess what happens to a gas when it gets cold. I'm melting, oh, what a world, what a world. And you see that it melts down pretty far. And then, of course, when you warm the gas back up, it's alive. I like old movies. But so if you think it gives you an idea of just how cold the liquid nitrogen is, that it can actually liquefy the air that was in the balloon. It not only made it contract, it got it down to a liquid too, because the air is mostly nitrogen.
Oh, yeah. Slow them down.
No, not in the mic.
Yep.
You're welcome. Doug, is it time for the finale?
It is time for the finale?
I think it is time for the finale, isn't it?
Yes, no,
No, I got you.
okay, yeah.
Okay, so Doug and I were trying. Now, I got to say, we have had a blast working on this, and we feel like we barely scratched the surface. We were trying all sorts of stuff over in my lab and over in the central kitchen, and it was hard to cut it down. So I don't know. You guys want to do this again?
Yeah.
Oh, okay. Well, I think they want to do it again. Whoopsie. There was one other demo. Now, this one we're not going to be able to serve for you guys, but I thought we would give it a try to demonstrate for you anyway. We're going to do yogurt pretzels flambe
I got one more on the counter out here.
a la liquid oxygen.
Yeah. Now, if you're wondering why your ice cream is so hard, I put it in the freezer, and I was afraid of it melting on you, so I packed it in dry ice and left it in there for a couple hours. And so we were demonstrating the efficiency of dry ice on ice cream. So I meant to do that. So, yeah. Right? I planned it, right?
Planned it, yeah.
Thanks, Janie.
Good save, Doug.
Okay. Should I put on my
Can you hold this?
goggles? You bet.
All right, so what we're going to do here, hold it close. What we're going to do is we've got yogurt pretzels.
Sorry? Oh, no. I'm staying out of the way.
You never can get these things open. Why do they make them?
Oh.
Yeah. Okay. We're going to take some ethanol, ethyl alcohol. Let's get that somewhere far away. Then we're going to cool down this crystallization dish to liquid nitrogen temperature using liquid nitrogen. Let that cool down for a little bit. You'll be able to tell when it's cool, it'll stop boiling. Now that the dish is cool, I'm going to get rid of the liquid nitrogen. Look out, guys. Now I'm going to put some liquid oxygen in there. Liquid oxygen liquefies at a temperature a little bit higher than liquid nitrogen so that you can actually use liquid nitrogen to condense it. And I made it back in the lab today. Can you believe they trust me with the lab? Now, let's see, yogurt, I can't either. Yogurt pretzels flambe. First of all, a little bit of alcohol. Can someone light this for me? You have to dip it in the liquid nitrogen.
Oh,
Do that
liquid,
with the
let's do it
nitrogen.
again. Yeah.
We'll have to do it
We have
again.
more.
Let it cool for a second. Like that.
Flambe.
Yeah. Too long? A little bit too long. Okay. That was yogurt pretzel burn. Al carbone.
Cajun style.
Cajun style. So I think we can avoid that maybe by cooling it down a little bit beforehand. Let's try that.
Is that ice cream
I like
softening
having
up?
you as a safety consultant. I think this is really good. Now, let's try that again. Let's put it in the alcohol. Light it. I think that's better. More light? All right. What is it? I mean, you're a chef. Tell us.
Like a yogurt covered pretzel dipped in alcohol.
Doesn't get any better than that. All right. Thank you very much.
All right. Okay, set it up. All right.